We are Group 55 and the team members are Ongshu, Karanjot and me, Rupam Goldar. Our project is retail sales forecasting with classical and deep learning models. In simple words, we built a system that guesses how many items will sell using past sales, and this helps the shops keep the right stock, avoid the loss of sales, and plan the revenue. We try two kind of models: a random forest, many small or yes not trees body, and a LSTM, a neural net that can remember sequence. Also made a Streamlit web app so anyone can try the forecast. Now moving on to the slide 2, which is the background and objective. In real stores, the sales go up and down with price, discounts, promotions, and special days. Our goal wasn't only to predict, but also to learn what really changes the sales. So we asked many questions. Do price and discounts really matter more than anything else? Do competitor prices pull our sales down? Do simple models beat the LSTM or not? Can we make a simple tool that the manager can use? These questions shaped everything that we did. Moving on to the next slide, which is the data set. We used about 650 rows with 30 columns. The target quantity, how many units were sold in a transaction. The key inputs were the unit price, what the customer paid per item, our main signal. The PS1 AP1 switches that tells us if the promotions or the featured placement were on. The comps/1 a competitor price to see if the lower rival prices hurts us. The lag price, the last month price, to capture the most recent price memory. The month, year, holiday. The time cues that we kept through current, though the time coverage is very small. The product category, groups like electronics versus furniture. Data types were very mixed, so we did a basic cleaning, encoding, and scaling first. Now moving on to the next slide, which is the unit price distribution. When we plot the unit price, it's the right skewed. Many items are cheaper, a few are very expensive, some are greater than the $300. Skew can confuse the model, so we also used a log of price that makes the shape more balanced and learning more stable. We noticed that the common price classes were around $50, $100, and $150, which may be psychological price points. The log view reduces the effect so that the model focuses more on the real patterns. Now, moving on to the next slide, which is the EDI insights. So the quantity per sale is usually around 1 to 5 units with a few big orders, because revenue is equal to price into quantity. So revenue also has a long tail. A few sales also make a lot of money. What that meant for us is that prediction must handle the skew. Logs can help. In that case, log into quantity. There are high value products which we should treat more carefully. Interactions like price into promotions can also add useful signals. These were the main insights of the EDA. Now moving on to the next one, which is the extreme value detection via percentiles. We check the key percentiles to understand the extremes. 75% of the prices are below $129.99, which means around $130, and the top 1% goes near around $350. The 99% of the quantities are below 82. Instead of deleting the points, so we use this as a reference gaps and use the log transforms. So this kept the data while making models more stable. Now moving on to the next slide, the temporal trend analysis. We only had 2 months, the January of 2017 and the January of 2018. Not enough for our real seasonality. Still two small signals. Average price dipped from $112 to $101, and the average quantity rose from 13.5 units to 15.3 units. This hints that the lower price can mean slightly more sales, likely helped by the promos, but with only 2 points we can't generalize that. Moving on to the next slide, price quantity relationship and elasticity. We plotted the quantity versus price. Most actions were where the price is between $50 to $150 and the quantity is under 20. A few bulk buys exist, likely promotions or special orders on a log-to-log plot. A quick line feed gives a slope of 0.131. So when the price changes a bit, sales barely changes. people buy about the same amount of units. That's the weak price sensitivity in this data. So to predict well, price alone isn't enough. We must include promotions, competitor price, recent price, and product category as well. Moving on to the next slide, the elasticity analysis. We used using these lessons, we trained a random forest and an LSTM. By doing the random forest, we gained mixed data and outliers, and the LSTM was helpful when sequence patterns mattered. We used cautiously due to the limited time coverage. Finally, we deployed the winner in a Streamlit app so a manager can select a product and set the price promo and see the forecast instant. And now my group member will follow up with the rest of the slides. Thank you.
Hi everyone, I am Karan Singh and today I am going to share my presentation. So first of all, correlation heat map basically that is price and promotion features. So moving into the analysis of our features, we first looked for simple linear relationships with our target quantity sold. The correlation heat map revealed a key insight all of our pricing and promotional features, including the unit price, competitor prices like competitor 1 and promotional flags like PS1 showed very weak linear correlations with quantity. The values most fell between minus 0.10 and positive 0.04. This tells us that a simple single feature analysis will not be enough. The true predictive power must lie in non-linear interactions and more complex modeling techniques which validate our decisions to use both tree-based models and deep learning. So in next slide, uh, and this is basically price elasticity. We explored the price relationship further by looking at competitor prices. The scattered plots confirm the low correlations. There was a no clear trend to show that an external price shift immediately impacts our sale quantity. Then we estimate price elasticity across products. So in this slide, we found huge variation in sensitivity with most products clustered between -2 and +2. This result was a big flag for us. It cautions against using a single global elasticity assumption. Instead, it strongly supported our plan to model demand at a more granular product or category specific level. So next is Pareto graph. So in Pareto distribution and revenue drivers, our final EDA insight was on revenue concentration. We found a classic Pareto or long tail distribution. Just the top 10 SKUs generated nearly 44% of all revenue. Products like Health 2 and Computer S4 were critical drivers. This concentration validated our strategy to eventually use segment level forecasting. We'll need premium analytics for the high impact SKUs and simpler approaches for the long tail. So next is data cleaning and feature foundation. With these insights, we moved into the core data pipeline. First, data cleaning and feature foundation. Uh, we removed impossible or negative values and exact duplicates, resulting in 676 clean records. We also successfully decomposed this month year field into usable time features. Uh, Next, we focused on handling extreme. To stabilize our models, we applied Winsor style capping using the 99th percentile for both price and quantity. This preserved the dataset structure while minimizing the influence of rare extreme outliers. Finally, um, for model preparations, we set up a robust two-track approach, tree models, and random forest. We kept numerical value features unscaled since tree models are scale invariant. Linear model, that is log regression, we performed a time pair split training on and past data and testing on future. Then we applied one hot encoding for our products categories and they used log transformation on price and other positive numerical value features. This log formulation was critical as it allows the linear model's coefficients to be directly interpreted as price elasticity. So this was my presentation. So I am welcoming to my next team member. for handling the presentation, and thank you for listening.
Hello everyone, my name is Vikash Munal and my ID is 371516. Now we will start from the model building part of our project, and we begin by testing five regression models, and our baseline model was a log linear regression model which is ideal for estimating price elasticity. We also added decision tree, random forest and gradient boosting to capture the non-linear patterns. We also tested the MLP regressor, which is a shallow neural net, and we use it for to if we can find any deeper relationships. In the next slide, you can see all the model evaluation results. Here we have used mean average error, root mean square error, and R square for evaluations. Now, surprisingly, the linear log model outperform others in mean average error and RMSE, though it has slightly negative R square. And as you can see, it's estimated the price elasticity at minus 2.33, meaning a 1% price drop would lead to a approximately 2.3 increase, 3% increase in demand, indicating moderately elastic behavior. The three-bit smaller models and MLP didn't perform well, likely due to limited data size and feature response. Now, in the next slide, here you can see the price and profit curves. Using our base model, the log linear regression model, we simulated two curves. On the left, the demand curve comes from the standard economic logic that higher price reduces demand, and on the right side, the profit curve peaked at $118, indicating the optimal price point under the assumed cost. Now, these curves actually enables strategic pricing by helping retailers estimate the demand sensitivity and take smarter promotional decisions. So, and these two graphs actually demonstrate that how our aim isn't just about the prediction, it's about driving smarter business decisions in real world retail pricing. We have also implemented LSTM, RNN, and GRU, these three deep learning architecture to check if they perform better than the classical ones. And for that, we have scaled the features and hard coded the categories and used Keras's time generator, time series generator to form five-step sequences. And we use 10H, RLU, and Adam and RMS prop optimizers in the combination of these three deep learning architecture. We also added dropout early stopping for stability and generalization, and all the models were evaluated through RMS. Here you can see the evaluation results, and the base model was the LSTM with 10H and RMS prop one, scoring a score of 13.47 and slightly positive R square. GRU came close, and RNNs actually underperformed, likely due to vanishing gradients and shallow memories. Now, 10H consistently outperformed RLU, and RNS prop worked better than the Adam optimizers for our short sequences. And across all the classical and real models, LSTM with APN, 10H, and RNS prop stood out, and we locked it in our final model for downstream images. Now, the predicted versus actual plot on our final LSTM model shows that LSTM tracked our baseline demand very well, but smoothed out on extreme spikes, likely due to the low support for rare events. And on the right, the loss curve shows the clean convergence with stable validation loss, indicating there was no overfitting and a strong generation. Now, while promising, our model had some certain limitations, like the deep learning was constrained by small dataset size, the extreme quantity specs were underfit due to low frequency, also the placeholder costed limited profit accuracy. And to solve all of this, we plan to end these features with promotions and other new data, and experiment with new models like BioLSTM and deploy the system via dashboards for business case users. Now, as we have listened through all our presentation, we applied both classical and deep learning models to forecast demand and optimize pricing. And the LSTM 10 with 10H RMS prop was the best performer in both accuracy and reliability. And as you have seen, this project is not only that predicts the demand, but it also empowers the retailers to make data-driven pricing decisions, building the foundation of a real-world pricing. Now, thank you all, and now we are happy to take your questions. Thank you.